learn about circular motion? Yes, it is. So let's get started. We'll approach the circular motion topic with pre-existing knowledge of linear motion. What we'll do is we'll have linear motion that we have already studied as a guiding point to explore concepts of circular motion. So this is a nice way to learn easily the circular motion and also to recap on the concepts about linear motion. What we define in linear motion is linear displacement in any one axis by a variable x, where x denotes position. And similarly, if we do define velocity, we define it with respect to position as dx over dt. That is exactly the same as saying rate of change of position is defined rate change of position is defined as okay. So let's talk about the counterparts of linear position in angular terms. Like what could denote a position of a particle that is going a circular motion? Of course, it would be angle with respect to a reference point, whether clockwise or anti-clockwise. So in this case, what makes uh, at what position after some starting point. Okay, so how we can represent it as in a circular motion. Suppose this is the particle and it is from the center at r distance, and suppose this is the point on the circle that we consider as a reference point. So with respect to this is reference. So with respect to the reference point, how much angle the object has made. So this is the position of object, but here we are not talking about linear position, but we are talking about the angular position, and that is how much angle theta angle. This is still an incomplete description because this theta could have been in the clockwise direction. If I don't tell you a diagram, then that would mean some position that is not the position we are talking about. So but to have a complete description, we will write that this theta is anti-clockwise with respect to reference point, that is this. So we have an object, let's make this with red, that is undergoing a circular motion, and we have correctly defined its position with respect to the green point, that is reference point. And what we can do next is to try to define just like linear velocity, that is v here, and linear position, that is just position denoted by x coordinate. So same way we can actually go on defining angular velocity, and angular velocity would mean, what could it mean? So drawing a reference from the linear velocity, as linear velocity means the rate of change of linear position with respect to time, or rate of change of position with respect to time, and that is given by position is in meters, so meters per second. So similarly, angular velocity will be defined as rate of change of angular position with respect to time. And what it would mean is The units will be radian per second. Okay, and that is how we have defined the equivalent of position in circular motion and equivalent of angular speed or angular velocity in circular motion. Just like velocity was defined as rate of change of position, similarly we can define acceleration as rate of change of velocity with respect to time. And the units will be velocity, that is meter per second, divided by per second. So it will be meter per second square. How about a circular counterpart of certain thing? What would it mean basically? A circular object in circular motion speeding up. What could it mean? It will rotate faster, or it will go on around the time in lesser around the circle in a lesser amount of time. So from here we can define that the rate of change of angular velocity is angular acceleration. So angular acceleration is d omega by dt. So in this case we have defined, so it should be omega here. So I'll make omega later. It will be rate of change of angular velocity with respect to time. And what will be the units? The units will be the same, per second, rate of change of radians per second per second. Radians per second square. All right. When a particle is in circular motion, it will have some tangential velocity. The tangential velocity is represented by blue arrow over here, and what it represents is a component of velocity that is at 90 degrees to the line joining the particle and the axis of rotation. One thing to note over here is the axis of rotation, suppose, is outside the plane. So this is a circle with a dot that represents something outside the plane, that is making 90 degrees with the line joining the axis and the particle, and that again is in 90 degrees with the line joining the axis and the particle with respect to velocity. So we have a orthogonal set of vectors in which axis axis is perpendicular to both velocity vector and line joining radius vector. I'll say the line joining or the positions connecting the axis and the particle is radius vector. So similar thing can be said for all of them. That means velocity is also perpendicular to axis as well as radius vector, and that also implies that radius vector as is again perpendicular to both of them, the axis as well as velocity vector. So what it could imply? Have we seen certain three vectors that are perpendicular to each other? Yes, we have seen it. That is nothing more than the spatial dimension we live in. We live in a spatial dimension where there is three coordinates x, y, and z perpendicular